question is having a smooth hemispherical ball. Inside the ball, a small bead is projected in a horizontal circle with a velocity v naught say, so that it will move in a helical path and come to the highest position, at the top of the ball. We have to calculate the value of v naught. The initial angular position of this particle is theta with respect to the horizontal diameter. Now we have to see what are the concepts we can use. You take this is the y axis, draw the FBD. When you draw the free body diagram, this particle is acted upon by the gravity and the normal reaction. Normal reaction acts and passes through the center of curvature of the ball, and the gravity and the normal reaction, these two forces are acting on the particle. The normal reaction passes through this point C. Therefore, it cannot produce a torque about the point C, but the gravity can produce a torque about this point. Therefore, about this point we cannot conserve the angular momentum. About see, the gravitational torque is not equal to 0, because the magnitude wise gravitational torque is equal to mg into x. In which direction? In inward direction. Its magnitude is mg into x. That is not equal to 0. Well, therefore, the angular momentum of the system about this point C cannot be conserved. You cannot apply the conservation of angular momentum about this point. If you take this axis, y axis, which passes through the point of or center of curvature, the point C. If you take any point on the axis or about the axis, the torque produced by the normal reaction is 0. About the axis, which axis? Vertical axis, y axis. Torque due to the normal reaction is 0 and torque due to the gravity is 0. Why? You take any point P on the axis. About this point, the torque due to the gravity is always horizontal. This is the gravitational force mg. This is the r vector. R cross mg at this point is in. If you take the point here, this is mg, this is r cross mg will be out. So, the torque due to gravity, will rotate as the bead moves. The torque due to gravity will rotate about the y axis, and torque is entirely horizontal. The torque due to gravity is horizontal, since torque due to gravity is horizontal. Its component along y direction is 0. So, the gravity torque about the y direction is 0. About the vertical axis, there is no torque due to gravity. And what about the normal reaction? The normal reaction will produce a torque not about this point, but about any other point which does not pass through the line of action of the normal reaction force at this point. About this point P, the normal reaction will offer a torque that is equal to normal reaction into this perpendicular distance. The direction is in. At this point, normal reaction is n, and the direction of the torque produced by normal reaction when the particle is here, suppose, is out. This means that the torque produced by the normal reaction is acting parallel to z axis. Therefore, torque produced by the normal reaction along y direction is 0. So, the both gravity and normal reaction will have 0 torque about the y axis, about the vertical axis. Since torque is 0 about the vertical axis, angular momentum about the vertical axis remains conserved. You can conserve the angular momentum about the vertical axis, because about the vertical axis or the y axis, the particle will not experience a net torque. Now, we have to equate the angular momentum at this point and angular momentum at this point. At these 2 points, point 1 and point 2, angular momenta are equal along y direction. At this point, the angular momentum will be, say, m v naught into x. Let it be x. So, initially angular momentum is m v naught into x. In which direction? Along y direction. Since it is revolving in this way, the angular momentum is down, minus j k. After reaching the highest position, the angular momentum will be equal to m v naught, and this position, at this position, the distance, the perpendicular distance from the axis is none other than the radius, and which the direction will still remain downward, because to conserve the angular momentum, we have to conserve both the magnitude and direction, and you will get the equation v naught x is equal to, here let be v, it is not v naught, v into r, equation number 1. Since the hemispherical surface is smooth, since the smooth hemispherical surface, or for the smooth hemispherical surface, the frictional force will be equal to 0. So, there is no non-conservative force. When there is no non-conservative force, we can apply the conservation of mechanical energy. Here mechanical energy can be conserved, or you can apply the work energy theorem also. Here velocity is v, here velocity is v naught. This is x and this is r. The work done by gravity is equal to change in kinetic energy. Normal reaction cannot perform any work because always the normal reaction in the displacement, because the particle moves along the inside surface. Inside surface and normal reaction both are perpendicular. Therefore, the displacement of the particle on the inside surface and the normal reaction will be always perpendicular. Therefore, work done by normal reaction will be 0 and gravity will do work, because when it moves up through a vertical distance y, the work done by the gravity will be equal to minus mgy, because it is going against the gravitational force, will be equal to change in kinetic energy equal to final kinetic energy half mv square, initial kinetic energy half mv naught square. This is one way, or you can just conserve the energy because there is no friction, the surface is smooth. Del u plus del k is equal to 0. When it is moving from this position to this position through a height y, the change in gravitational potential energy will be equal to plus mgy. Change is always final minus initial, plus change in kinetic energy half m final velocity square minus initial velocity square will be equal to 0. Both the equations are same thing. Either you can apply the work energy theorem or you can apply conservation of mechanical energy. Any one principle you can apply. Where y is equal to this is r, the sine of theta into r, y is equal to r into sine theta. Substituting y is equal to r sine theta, we are getting mg r sine theta plus half m v square minus v naught square is equal to 0. This gives us v square is equal to v naught square minus 2gr sin theta, equation 2, where x is equal to r, because if this is x, this is theta, x will be equal to r cos theta. So, in the equation 1, you can still simplify this, v naught into r cos theta is equal to v into r will be getting cancelled to get v equal to v naught cos theta. This is equation number 1. And you are getting the equation 2. We are having 2 equations and 2 unknown quantities. What are the unknown quantities? V and theta. Just we can solve for this 2. So, from equation 1 you substitute the value of v. From equation 1, substitute v equal to v naught cos theta in equation 2 to get v naught cos theta square of this is equal to v naught square minus 2gr sin theta. And here for a given theta, we have 2 unknown v and v naught, initial velocity and final velocity. So, this will give us v naught square 1 minus cos square theta is equal to 2gr sin theta. So, v naught is equal to 2gr, 1 minus cos square theta is equal to sin square theta, and you are getting cancelled, and you are getting sin theta in the denominator, square root of this. And if you want to calculate the velocity at the top, that you can calculate, v equal to v naught cos theta. So, 2 gr by sin theta square root of this into cos theta answer. So, we can calculate v naught and v. Sometimes they will ask you relatively easier question. Instead of pushing the particle horizontally, you are pushing the particle horizontally with some velocity such that it will follow the spiral path or it is helical path about the vertical axis and go to the periphery of the highest point. Sometimes they may ask the question, sometimes they may ask you that instead of pushing it in horizontal plane, horizontally, you push it vertically or push it along this tangent such that it will move in a vertical plane. If the particle is projected with v naught so that it will move in a vertical plane, find v naught if the particle goes to the topmost position to reach the highest position. A relatively easier question. By energy conservation, you can get the answer. To go to the highest position, its entire velocity will be adjusted. So, the final velocity will be 0 instead of non-zero value. That non-zero value will be this much. So, here the change in kinetic energy will be equal to work done by the gravity plus work done by normal reaction. Normal reaction does not perform any work because normal reaction is perpendicular to the displacement. Always it may move in vertical circle or it may move in a spiral path or helical path, does not matter. Always the displacement of the particle along the plane in any direction is always normal to the normal reaction force. Therefore, the normal reaction force will never do any work for this case, and work is done by the gravity only. When the particle moves from position 1 to position 2, gravity does negative work, that is equal to minus mg y is equal to change in kinetic energy. Final velocity is 0, initial velocity is v naught. So, v naught is equal to 2 g y square root and y is equal to, here y is equal to r sin theta. You substitute y to get 2 g r sin theta square root of this. It is very interesting to note that in this problem you are getting the square root of 2gr upon sin theta. In this problem you are getting the square root of 2gr sin theta. It is a relatively easier problem where you are only conserving the energy. Here you can conserve the energy. So also the angular momentum, not about this point but about the axis passing through that point. Let us go for next example. Let us find the angular momentum of a system of two particles. Find the angular momentum of a two particle system. If the particle 1 having mass m1 moves with velocity v1 and particle 2 having mass m2 moves with velocity v2 with respect to ground respectively. And the position of or distance between these two particles, let be r. To solve the problem, let us assume that particle 1 has position vector r1 with respect to this point and particle 2 has position vector r2 with respect to the same point. The total angular momentum of this two particle system about any fixed point LO is equal to angular momentum of this two particle system about the center of mass plus angular momentum of the center of mass. We are not interested in this. We are interested in this is the spin angular momentum and this is the orbital angular momentum. We are not interested in calculating the orbital angular momentum. We can calculate the spin or the internal angular momentum of the system of two particles. So, find the angular momentum of a two particle system about or with respect to its center of mass. So, I'll see how to calculate. For these two particles, this is the center of mass, say this is r1. See the position vector of the first particle with respect to the center of mass, and this is the position vector of the second particle with respect to the what? Center of mass. Its velocity with respect to the center of mass, let be v1c, and with respect to the center of mass, its velocity let be v2c. The angular momentum of the system with respect to center of mass will be equal to angular momentum of the first particle with respect to center of mass plus angular momentum of the second particle with respect to center of mass. L1c is equal to R1c cross M1 V1c. L2c will be equal to R2c cross M2 V2c. R1c and R2c are the position vectors of the particles with respect to the center of mass, and V1c and V2c are the velocities of the particles with respect to center of mass frame. We know that m1 r1c plus m2 r2c is equal to 0, and m1 v1c plus m2 v2c is equal to 0. As I explained you, the property of center of mass, because m1 r1c plus m2 r2c is equal to m1 plus m2 rcc. m1 v1c plus m2 v2c is equal to m1 plus m2 vcc. Since position vector of the center of mass with respect to center of mass is 0 and velocity of center of mass with respect to center of mass is 0, these terms will vanish. Therefore, we are having this expression and this expression. These expressions will be the expressions for the sum of the momenta of the particles, and the second expression is the sum of the momenta. This is the moments, it is the momenta. M into R is the moment of mass, M into V is the momentum. Sum of the moment of mass with respect to center of mass will be 0. That is the property of the center of mass. And sum of the momentum of all the particles with respect to the center of mass is always equal to 0. That is another property of the center of mass. With these ideas, we can write m1 v1c is equal to minus m2 v2c, or m2 v2c is equal to minus m1 v1c, or you can write m1 r1c is equal to minus m2 r2c, or m2 r2c is equal to minus m1 r1c. So, both the ways we can solve the problem. LC is equal to, about the center of mass, the angular momentum of the system of two particles is equal to r1 cross m1 v1c plus r2 cross m2 v2c. If you write m2 v2c as minus of m1 v1c, without disturbing the first factor, we are getting m1 v1c, you take common. When you take common, you are getting r1 minus r2 vector cross r1 vector minus r2 vector cross m1 v1 vector minus vc vector. v1 vc is equal to m1 v1 plus m2 v2 by m1 plus m2, velocity of center of mass r1 minus R2 is equal to R1 to the position vector of 1 with respect to 2. R1 to cross M1, V1 into M1 minus M1 V1 will be getting cancelled. You are getting M2 into V1 minus M2 into V2 vector by M1 plus M2. After simplification, you are getting R1 to, take the scalars out, this will be M1 M2 by M1 plus M2, R1 to cross V1 minus V2 can be written as V1 to velocity of 1 with respect to 2, because V1 minus V2 is equal to V1 2. So, this is the angular momentum of the system with respect to the center of mass. Sometimes we call it reduced mass, mu R12 cross V12 LC. Or we can write LC is equal to position vector of 1 with respect to 2 cross mu velocity of 1 with respect to 2. In this way also you can write, in this way also you can write, in this way also you can write. So, we have used this expression in this expression. We can use this expression to get the same answer. Well, let us use this second expression. By using the second expression, we can write M2 V2C is equal to minus M1 V1C, or you can write M1 V1C is equal to minus M2 V2C and substitute in this equation. LC is equal to R1 cross M1 V1C plus R2 cross M2 V2C. M2 V2C, well, using the first term also we can solve the problem. M1 is a scalar quantity, M2 also is a scalar quantity. So, you can take M1 to this side, M2 to this side to get M1 R1 cross V1C plus M2 R2 cross V2C. M1 R1 and M2 R2, anything you can substitute. If you want to keep M1 R1 as it is and change M2 R2, you can write M2 R2 is equal to minus M1 R1C cross V2C. M1 R1 can be taken common. M1 R1C. You can take M1 R1C common cross V1C minus V2C, and this is equal to V1 2. Velocity of 1 with respect to 2 is equal to velocity of 1 with respect to any reference point, that is center of mass, minus velocity of 2 with respect to that reference point. R1C, M1 R1C. M1 R1C can be written as R1 minus RC cross V1 2. R1 minus RC can be written as M1 R1 plus M2 R2 by M1 plus M2 cross V1. That's equal to M1 R1 minus M1 R1 will be getting cancelled, and you are having the term M2 into R1 minus M2 into R2 by M1 plus M2 cross V12. If you take M1, M2 common, you are getting that reduced mass factor. R1 minus R2 can be written as R12 cross V12. Exactly same answer you are getting in the second method. So, V12 is the velocity of 1 with respect to 2 and R12 is the position vector of 1 with respect to 2. Therefore, the angular momentum of the system of two particles with respect to center of mass depends upon the relative motion or the relative velocity between these two particles and position of 1 with respect to 2 or position of 2 with respect to 1. You can write R21 cross V21 and it remains as it is. Mu is equal to mu R12 this is mu R12 cross V12, or you can just write mu R21 cross V21, because R21 will be equal to minus R12, V21 will be equal to minus B12. So, this term will remain unchanged. So, this is the expression for the angular momentum of the system of two particles with respect to the center of mass. Let us take the last example of two particles it's connected with the other particle. Its velocity is v. Its velocity is v. This velocity is perpendicular to the spring and this velocity is along the spring. This particle 2 moves along the spring and this particle moves normal to the spring in the same plane. Find kinetic energy angular momentum linear momentum relative to the center of mass of the system. Kinetic energy with respect to center of mass KDS is equal to half mu v relative square. We talked about this in center of mass of the system of particle. Mu is equal to m1 into m2 by m1 plus m2. V relative is equal to V1 minus V2. V1 is V I cap, V2 is V j cap. Its magnitude can be written as V square plus V square square root. So V relative square is equal to 2V square. 2 will getting cancelled. You are getting this factor will be m by 2 into V square. Answer. Second, the angular momentum about the center of mass is equal to mu r12 cross v12 or mu r21 cross v21. This is r12 vector. Let it be L is the distance between these two particles or length of the spring at this instant. That is L_J_K. X axis, this is Y axis. B12 is equal to V1 minus V2. That is equal to Vi cap minus Vj cap. So instead of V12 I can write Vi cap minus Vj cap. Instead of R12 I can write Lj cap. Position vector of 1 with respect to 2. So instead of mu I can write m by 2. m1 m2 by m1 plus m2. L. You take V out of the bracket, j cap cross I cap. I j k. I cross j equal to k. J cross k equal to I and k cross I is equal to j. J cross I. J cross I is equal to minus k. J cross j is equal to 0. Therefore, you are getting minus mvl by 2 kk. Or it is clockwise direction or it is in. The angular momentum of the system with respect to center of mass is inwardly directed or clockwise. Next, the linear momentum. The linear momentum with respect to center of mass is equal to m1 v1c plus m2 v2c, and that is equal to 0. Already you know as the property of center of mass, because m1 v1c plus m2 v2c is equal to m1 plus m2 into vcc, velocity of the center of mass with respect to itself, that is equal to 0. In this way, through these conceptual problems and illustrations and the theoretical details, we are acquainted with the use of these two terms, torques and angular momentum, applied for a particle or of a system of two particles or more than two particles. Then we can develop the expression for the law of rotation and law of translation for a system of the particles when these particles are glued together, so that the distance of separation between any two particles will remain the same. That is what is known as rigid body. So you can apply the concept of torque and angular momentum for rigid bodies in the next chapter.